OK, so there's one more step that we have to do before we start talking about the Lagrangian. And that's this little caveat that I had right at the beginning where I said, let's consider only quarks. So far, we've only considered the quark part, not the antiquark part. So let's see what we want to do about antiquarks. Technically, the way the field theory wants to work is that the quarks and the antiquarks kind of want to be different fields. But that's very cumbersome. And so we're not going to do that. And we're going to find, again, sneaky notation to treat them as one field, even though they want to be two. The reason that they want to be two is because if you look at the phase factor for the quarks and the antiquarks in the kind of standard mode decomposition, it has the opposite sign. So look at the mode expansion in QCD. I can write it in a covariant type notation where with a D4P, if I put in the proper projection, and then we have the quark part with the e to the minus I p dot x, and then we have this anti-quark part, or b daggers, and the e to the plus I p dot x. OK. So let me think of that as a psi plus plus a psi minus. And we've so far only talked about psi plus. So for psi plus of x, we have a sum over p l not equal to 0, e to the minus I p l dot x, of sort of a cn p l plus of x. And if we were to repeat everything we did for this, so this is the case we did. If we were to repeat everything we did for this case, then what we would get for psi minus, and this is why I say that they want to kind of look at like separate fields, is we'd get a plus I p l dot x. And in this notation, if you think about the P0 is the sum of the P minus and the P plus. So saying that in this mode decomposition, P0 is greater than 0 becomes, for these two equations, when we go over to sort of a linear scaling, becomes that PL minus is greater than 0 in these equations. OK, so that's the sense in which these are different. With a positive PL minus, we have an opposite phase factor for these two guys. And in both of these cases, it's true that, just as kind of a way of remark, we still have this. That didn't change. Remember. OK, but talking about minus and plus fields would just make our life really difficult. Actually, when we first derived SET, sometimes you're boneheaded. We went through everything in a much more detailed way than I'm going to present it to you now. Wrote out everything in terms of plus fields and minus fields because of this little issue. And then we noticed the following thing that I'm going to tell you, that we could just put everything back together with a simple definition. And that's because really the only difference is this sign. So if we want a kind of convenient notation, we can do the following. So far, if you like, we have this guy with PL is not equal to 0, but the PL minus should be greater than 0. And if we define, so we can make use of kind of negative labels by the following trick. Just define a composite field that looks like this, where I put the minuses and the pluses back together. If I have a positive PL minus here, then that's giving the pluses. If I have a negative PL minus here, then that's giving the minuses because of what I just told you. So we don't just think about this guy as having plus PL minus. We allow it to have negative. And we take the negative PL minuses as a way of encoding what's going on with this guy. So we have different possibilities for m bar.pl. And if you like, what the plus guy is doing is destroying particles. And so that's for the, let's say this is for the, if I think about Cn of PL, let me make my chart like this. If I think about what Cn of PL is doing, it's destroying particles, and the antiparticles are created. But the antiparticles are going to be created for the opposite sign of the PL, okay? And then if I think about what the barred field would be doing with this notation, if the m bar.pl is greater than 0, then the particles are created. So this guy is really just the field we were talking about before if PL is greater than 0, and if PL is less than 0, it just repeats the whole story for the antiparticles. Okay, so I could write everything out in terms of this plus and minus field, but if I just make this simple definition, put everything back together and just work in terms of one field, which kind of does what we're used to. And there's just a sign convention to remember for this PL. And that sign convention is also easy to remember because the PL is really following the fermion flow. If you think about a fermion, right, then if you think about the physical momentum of that fermion, then the physical momentum follows the fermion in the case of the fermion, and it's opposite to the fermion in the case of the antifermion. So here's a fermion coming into some vertex. Here's an antiparticle coming into the vertex. And the PL goes this way. It follows the fermion flow, whereas the physical momentum is going this way. Okay, and that's the sign we're just keeping track of. And so the P labels are always following the arrows of the fermion lines. They're always along the fermion number with the conventions we've set up. Okay, so with that little piece of notation, we take into account the antiparticles as well. There's no real additional complications, since it's always really clear from, anyway, from if you draw a picture, it's completely clear what's an antiparticle and what's a particle, and it just follows your intuition. And furthermore, because the only difference in the mode decomposition was that sign, and we've now accounted for it by just making the labels negative, we have this equation too for both particles and antiparticles. So we get the opposite phase here because this guy has the opposite sign. So there's really no additional complications from adding the antiparticles once we set up this notation. Okay, any questions so far? What about linear gluons? So the gluon field is Hermitian, the original one. And what does that translate into? Well, it translates into the B's and the A's, right, both appearing in the decomposition of the field. There's no B's, they're just A's. And if you work out using the type of mode decomposition that we're doing and using the type of notation that we're doing, what that means, it means that this star of this guy just flips the sign. So that's what hermiticity of the original field becomes for this notation. And again, you can think of, you could think of associating, because of the theta functions that show up in the mode decomposition, you can think of associating QL minus greater than 0 as sort of destruction, and then QL minus less than 0 as creation. If you want, although it's not absolutely necessary, you could adopt this convention, and then that would just be putting a particular direction to your gluons And everything that we said before goes through. And in particular, if we think of decomposing sort of the hatted version of the fields, then this, just like before, and we can just also, again, as before, if we like, adopt a notation where we suppress the labels if we don't need them. So the gluons, really, there's nothing. In some sense, it's just simpler because we don't have to worry about the particles and the antiparticles because of the hermeticity. It's sort of they're all the same thing. And for most purposes, there's no sense in even keeping track of this convention. So that's why I went through it quickly. Because the convention is always kind of obvious from the context, whether if you're really talking about production of a real gluon or annihilation of a real gluon, then you can keep track of the signs that way. The fermion's a little different. So because any starred field is just the negative of this guy, we could always write everything in terms of fields that have no daggers for the gluons. But for the fermions, some of the fields are barred or daggered. OK, so what would be the form of having a general label operator act on some combination of daggered fields and some combination of undaggered fields, where the gluons are always undaggered? Well, it just gives the sum of these momenta. And the way it does it, the sum of the label momenta. So I'm thinking of all these denominators as label momenta. And maybe not put the L. And the way that the convention works is that we get a minus sign for the daggered guys. That's our sign convention. And the reason for that sign convention is effectively that if you think about e to the minus I curly p dot x on some phi of p1, and then you take the dagger of that, right, then it becomes phi p1 dagger of e to the plus I kind of p dagger dot x. And basically, I'm saying that I want to be able to write that as like this. And that convention is useful. So if I want to act forward on this field, which is a daggered field, then I'm going to take the opposite sign. And if I have a daggered p, then it would take the plus sign. And that convention is the useful one for keeping track of momentum conservation. Because then every field has the same convention. We just have e to the minus I p dot x for every single field. All right. So if we started with some partial derivative, some regular derivative, and it was acting on one of our hatted fields. So if I write it out in terms of the labels, put a PL on it, like. We'd have that. And so there's two contributions from this derivative. It either hits the phase or it hits the field. And so we can write it like if we go over to the label operator, we can write it this partial derivative as a sum of two derivatives. Which then we can take the sum over PL inside and write it as. So every derivative the purpose of this exercise is to convince you of the sanity of the notation. Every regular derivative acting on one of these Hadad fields where we hadn't yet decomposed momenta just becomes a sum of these two derivatives, and that's just like the fact that we split the full momentum into the sum of the label and the residual piece. Okay, this is the field version. Of p mu equals p L mu plus p residual mu. Okay, but the advantage of this notation is that we can then drop the partials if they're smaller. That's the whole reason for this setup.